Hi, I'm Bob. Welcome back to the tutorial on the exercises and applications for the textbook Econometric Analysis, the 8th edition by Professor William Greene. Today, we will continue solving the exercises for Chapter 4, Estimating Regression Model by least squares. It is Father's Day today. I am grateful to my father, who taught me to become a man of perseverance, resilience, and self-discipline, not only by his words, but also by his actions and examples. In exercise 5, we will prove that the least squares intercept estimator in the classical regression model is the minimum variance linear unbiased estimator. We can show that the least squares estimator under classic linear regression assumptions has the smallest variance among all the linear unbiased estimators. Not only the intercept estimator, but also the slope estimator has the minimum variance. The OLS estimators are the best linear unbiased estimators, blue. We write down the regression model in matrix form. The error term epsilon is uncorrelated with the explanatory variable x and has a constant variance of sigma squared. Suppose another linear estimator of beta is beta tilde. It can be expressed as a linear function of y, where D is a k by n matrix, and it is a function of x. The next step is to write down beta tilde's expected value. We replace y with its equation. There were 4 terms. The second and the fourth terms equal 0 by the zero conditional mean assumption. 2 terms are left. Because beta tilde is an unbiased estimator of beta, the expected value of beta tilde equals beta, which leads to d times x equals 0. The third step is to write down its variance. There were 4 terms. Because d times x equals 0, and the variance of a parameter is 0, the variance of beta tilde can be simplified to 2 terms. The first term is the variance of the least squares estimator b. The second term is sigma squared times d prime. The difference between the variances of beta tilde and b is sigma squared times d prime. We can show that it is positive definite by the definition. Therefore, the variance of beta tilde is greater than the variance of b. We know that the diagonal elements of a positive definite matrix are positive. The upper left diagonal element is the difference in the variances between the intercept estimators. It is positive, meaning that the variance of any other intercept estimator is larger than the least squares intercept estimator. The OLS intercept estimator is the minimum variance linear unbiased estimator. Similarly, we can show that the OLS slope estimator also has the minimum variance among all linear unbiased estimators. Let's solve exercise 6. A profit-maximizing monopolist faces a linear demand curve. A sample of price and quantity is given. Based on the least squares regression, compute a 95% confidence interval for the expected value of the profit-maximizing output. We solve the problem in 2 steps. In the first step, we figure out what we need to compute to answer the question. Suppose we obtain the least squares estimators, alpha hat and beta hat. The expected quantity is alpha hat plus beta hat times P. We can write the expected profit pi hat in terms of alpha hat, beta hat, and P. The first order condition for maximization is the first derivative of pi hat with respect to P equals 0. We can obtain the profit maximizing price P star and quantity Q star. They are functions of alpha hat and beta hat. Then we can find the variance of Q star in terms of the variance of beta hat, the variance of alpha hat, and the covariance between alpha hat and beta hat. The standard error of Q star is the square root of its variance. Finally, we can read the two-sided 5% critical value with 13 degrees of freedom in the t-statistics table, 2.16, and then construct the 95% confidence interval. So we need to estimate the alpha and beta using the least squares method. We do it in Stata in the second step. After we input all the data to variables constant P and Q, we can use the matrix form expression to compute the estimators. However, a more straightforward way is to regress Q on P. We type return list to find what estimates are stored in memory. The estimates of the coefficients alpha hat and beta hat are stored in the vector EB. The variance and covariance are stored in the matrix EV. We use the matrix list command to display these values. Now we have all the elements in hand. We can calculate the profit maximizing output Q star, the variance of Q star, the standard error of Q star, and the 95% confidence interval for Q star. Thank you so much for watching this video. See you soon in the following exercises. Goodbye. Thank you for watching this video and subscribing to my YouTube channel. See you next time.